Hey there, coding legends. Welcome to what might just be the best Pacman tutorial in the universe. Get ready to dive into the world of dots, ghosts, and coding awesomeness as we build a classic Pacman clone from scratch in C# and WinForms. This isn't just a tutorial, it's an adventure into code, fun, and retro gaming nostalgia. Grab your keyboards, buckle up, and let's do this. First, let's start by creating a new Windows Forms project in Visual Studio. We will create everything direct in code, so not need to create any layout for the game. Just coding. This is the class where everything happens, Pacman's movement, ghostly chases, and even those satisfying waka waka sounds. It inherits from Form, which means we get all the power of Windows Forms built in. Now it's time to declare Pacman's brainpower, our variables. We start at first with the base, the map for Pacman. For this we need tile size. Each block of the game grid is 30 pixels of fun. Level grid, our invisible map, where walls, dots, and Pacman live. Picture boxes, the grid's fancy clothes, every block gets a visual. First of all, we need the necessary data for a classic Pacman level. We will create a simple text file in the project resources and fill it with text. This is a very easy way to create or modify the level. We use different characters for wall, dots, or later ghost and everything we need. With this method it is very easy to expand. I have already prepared a level that we can use. Feel free to create another one. The only important thing is that you use the same characters. So the hash is the wall and the dot we will use for the Pacman dots. That's enough for the beginning, we will expand it later. The load level method is essential because it transforms the blueprint of our Pacman level into something the game can understand and display. Think of it as translating a treasure map into a playable world. What does load level do? This method reads the level design, provided as a string, level data. Converts the string data into a 2D grid, level grid, that represents the game world. Prepares the groundwork for visualizing the level with picture box objects. I will explain it step by step after creation. Step 1. Declare a list to hold the map lines. First, we create a list string called lines_data. Think of this as a shopping cart where we temporarily store each row of the map as we read it. This makes it super easy to process the level row by row later. Step 2. Read the level data line by line. Next, we use a string reader to take the entire block of level data and break it down into lines. Here's how it works. We loop through the data, grabbing one line at a time using reader read line and add it to our list, lines_data. If a line exists, boom, it gets added to the list. If there's nothing left to read, we stop. This step is basically about turning one giant block of text into neat, individual rows. Step 3. Convert the list to an array. Now, we convert the list into an array using lines_data. To array. Why? Because arrays are faster and perfect for fixed size data like our level map. This gives us a clean, manageable structure to work with for the next steps. Step 4. Determine the map dimensions. Here, we calculate the size of our map. We grab the number of rows from lines. Length, which tells us how many lines are in our map. Then, we grab the number of columns by checking the length of the first line, line 0. Length. Now we know the size of the grid we're working with. Step 5. Initialize the grid and picture box arrays. Next up, we create two grids. One is a 2D character array, level grid, which holds the logic of the map, like where walls or dots are. The other is a 2D picture box array, which will later handle the visuals of our map. Think of it as building a frame before painting the picture. Step 6. Loop through each tile in the map. Finally, we dive into the map with two loops. The outer loop goes row by row, and the inner loop goes through each column in that row. For every tile, we grab its character using lines row call, and save it in level grid row call. This step is like assigning each square in the grid its identity, wall, dot, or empty space. And voila! Our logical map is ready to roll. So now that our level is loaded and our needed variables are set up, we can fawn on with the map creation using initialize game board. This will make it visual to the user together with the method update tile. Let's first code the complete part. After that I will explain every step for you. Because if you understand, you can later extend the method with own steps if needed. Step 1. Get the dimensions of the map first. We grab the number of rows and columns from our level grid. We use getLength0 to get the number of rows and getLength1 for the columns. This tells us how big our map is, so we know exactly how to set up the game board. Step 2. Resize the game window. Next, we adjust the size of the game window dynamically. The width is the number of columns multiplied by tile size, and the height is the number of rows multiplied by tile size, plus a little extra 50 pixels for things like the score or status bar. This way, the game perfectly fits any level size, no matter how small or big it is. Step 3. Create a picture box grid. Now comes the exciting part, setting up a grid of picture box objects. We start by creating a 2D array, picture boxes, with the same number of rows and columns as the map. Each picture box represents one tile in the game visually, like walls, dots, or empty spaces. Step 4. Loop through each tile. We loop through each row and column of the grid using 2 nested loops. For every combination of row and column, we create a new picture box to represent that tile. Step 5. Configure the picture box properties. Each picture box gets a size of tile size by tile size. Its location is calculated using the row and column numbers, ensuring each box lands exactly where it needs to be on the game board. And to make it look clean and organized, we set a fixed single border style. Step 6. Add the picture box to the form. Next, we add the picture box to the form with this. Controls. Add picture box. This step makes it visible in the game window. Step 7. Store the picture box in the grid. After adding the picture box to the form, we also save it in our picture boxes array at the correct position. This lets us easily update the visual appearance of any tile later. Step 8. Update the tile's appearance. Finally, we call the update tile method for each tile. This ensures that every picture box starts off displaying the correct image or color based on the game map. For example, walls might appear as solid blocks, and dots as small circles. Wrap up. And that's it. With just a few lines of code, we've set up a dynamic game board where each tile knows where it belongs and what it should look like. It's like laying the foundation for the ultimate Pac-Man playground. So let's explain the update tile method that is called from the initialize game board that we already explained. First, we retrieve the picture box at the specified row and call from our picture boxes array. This gives us the exact tile we need to update on the game board. Step 2, find out what's on the tile next. We look up the tile type from the level grid. Each tile is represented by a character, like hash for walls. For dots, or maybe something else. This character tells us how that specific tile should look. Step 3, use a switch statement to decide the look. Here comes the fun part, the switch statement. It's like a control panel for designing each tile based on its type. Step 4, case hash, the wall tile. If the tile character is hash, it means it's a wall. We set the back color of the picture box to blue, giving it that classic maze wall look. Step 5, case, the dot tile. When the tile is, it represents a dot or a pellet, one of those things Pacman eats. We set the back color to black, just like the background of the maze. But here's the magic, we also call a helper method, generate.image, to create an image of the dot and display it inside the picture box. Now, the tile visually looks like a tiny edible pellet. Step 6, the default case, empty space. Finally, if the tile is anything else, like an empty space, we go to the default case. Here, we also set the back color to black, but we make sure there's no image in the picture box by setting picture box image to null. This clears out anything that doesn't belong there. And there you have it. This method ensures that every tile in the game board looks exactly the way it should. Walls are blue, dots are displayed with an image, and everything else is a clean, black void. With this in place, the game board comes alive, giving you that classic Pacman vibe. Using the generate.image method, we create an own image from a kind of dot for Pacman. It's also possible to load there an existing image, but maybe this is also interesting for you. And no image needed at all. So let's jump through it. Step 1, creating a blank canvas. First, we create a new bitmap. Think of this as our blank canvas where we'll draw the dot. The bitmap is square shaped, and its size is defined by our tile size, so it perfectly fits into the game tiles. Step 2, setting up the graphics. Next, we fire up the graphics engine. We use graphics from image bitmap to link our blank canvas to the drawing tools. This graphics object allows us to draw shapes, colors, and more on the bitmap. Step 3, drawing the dot. Now, here's where the dot comes to life. We call fill ellipse, which draws a filled circle on our bitmap. First, we pick a color, brushes. Yellow gives it that bright Pacman-like shine. Next, we decide where to position the circle on the tile. By using tile size 3, we center the dot neatly within the tile, making it look proportional and polished. Finally, the circle's size is also set using tile size 3, ensuring it's small and snackable, just like a classic Pacman pellet. Step 4, returning the image. Once the dot is drawn, we simply return the bitmap. Now, this image is ready to be placed on any tile where we need a dot. Every time Pacman eats one of these, it's game on. Now it's time for a first test. Magic! If you see, there is a Pacman game map. Wow! Looks nice, or? If we see on our text file, we see it's completely related to our file. All the dots and walls are there. And it's also very easy to modify, or create a complete new map. Let's remove some walls and fill it with dots for a short test. After that is done, we can directly restart the game and see the change in our game map. Cool stuff. But something is missing in the game, or? Where is Pacman? Let's add the needed stuff to bring him alive. In order to add Pacman to the game, we first need a few new variables. One is from type point, and we will use it to track his position. And we also make a list that we fill with the positions of the ghosts so that we can track them too. Then we update our level. Simply add a P for Pacman anywhere and a G here and there wherever we want the ghosts to be. That's it. Simple, isn't it? If that is done, we can easily assign the positions to the variables in our load level method depending on the character P or G. Using this method and the text-based level design, we can easily add, change or remove almost everything that we need for our game or later extensions. If we start the game, you can see that there is empty space there where our Pacman and ghost had to be. That is because we need also update our update tile method. Here we can set the visual part for any game object. We have only to add the needed char to the switch statement and there we go. To paint our tile depend on the letter. So P for Pacman and so on. You could simply load an own image, or you can use my generate Pacman and generate ghost image method. We start by creating a blank bitmap, just like before. The size of this canvas is our trusty tile size, giving us plenty of room to draw our spooky little ghost. Next, we grab our graphics object with graphics. From image bitmap, this is our magical drawing tool to bring the ghost to life. First, we draw the top half of the ghost as a red circle using fill ellipse. This gives it that round, adorable ghostly dome. Then, we add the bottom half as a red rectangle using fill rectangle. It's like the ghost is wearing a flowing sheet, classic ghost vibes. Finally, we return the completed ghost image, ready to be placed in the maze. It's simple, spooky, and totally on theme for Pacman. Now, it's time to create the star of the show, Pacman. And trust me, this method is just as cool as Pacman himself. First things first, we create another blank bitmap. Just like before, it's the size of a single tile, so Pacman fits perfectly in our grid. First, we move the origin of our canvas to the center with Translate Transform Tile Size, 2, Tile Size, 2. Finally, we move the origin back to the top left corner with another Translate Transform. Next, we use Fill Pie to draw Pacman's iconic chomping shape. We pick brushes. Yellow for that unmistakable Pacman color. The 0, 0 coordinates mean we're starting right at the top left of our tile. The last two arguments, 30 and 300, control the shape of Pacman's open mouth. 30 sets the start of the mouth angle. 300 defines how big that chomp is. It's dynamic, it's fun, and it makes Pacman look ready to gobble up some dots. And that's it. We return the Pacman bitmap, with his mouth wide open, ready for action. These two methods bring life to our game. The ghosts add danger, and Pacman is the ultimate hero, always ready to chomp his way to victory. With just a few shapes and some clever rotations, you've got yourself a visually stunning Pacman game. So if we start now the game, we can see our hero and also the enemies from the game. Let's try as a next step to control Pacman. Alright, let's dive into the method that gives Pacman his moves. This is where the magic of navigation happens. Let's break it down step by step. We're overriding a method called process, CMD, key. Why? Because this lets us capture key presses directly, perfect for controlling Pacman's movement. It takes two parameters. Message represents the incoming message about the key press. Key data tells us which key was pressed, like the arrow keys. First, we create a variable new position to store Pacman's potential new position. We initialize it to his current position, which is stored in Pacman position. Think of this as testing the waters before we commit to a move. Next up, the switch statement. This is where we figure out what key the player pressed. If it's up, we decrease new position. Why? Because in our grid, moving up means decreasing the y coordinate. For down, we increase new position. Why? Pacman moves down the maze. If it's left, we decrease new position. X, shifting Pacman to the left. And for right, we increase new position. X, Pacman heads to the right. Each of these updates calculates Pacman's new spot based on the player's input. What happens if the player presses some other random key, like space or escape? Well, we handle that with the default case. Here, we call the base implementation of process CMD key, which simply ignores unsupported keys. This keeps our game focused and responsive. Once we know the new position, it's time to move Pacman. We call move Pacman new position, which handles the actual movement logic. This keeps our method clean and focuses this part solely on handling the key input. Finally, we return true to signal that the key press was successfully processed. This tells the program, yep, we've handled this input, no need for anyone else to worry about it. And there you have it. This method is like Pacman's personal GPS, processing your arrow key inputs and calculating the next move. With this in place, Pacman is no longer stuck, he's ready to explore the maze, dodge ghosts, and eat dots like a pro. So hit those arrow keys and let the adventure begin. Alright, it's time to put Pacman in motion. This method is like the engine behind his moves, making sure the game board stays updated as Pacman chomps his way through the maze. Let's break it down step by step. This method takes one parameter, new position. This tells us where Pacman is about to go next. Our job here? To update the game grid and the visuals on screen to reflect Pacman's move. Simple, but crucial. First up, we need to clear Pacman's current spot. Here, we're telling the grid, hey, Pacman just left this tile, so mark it as empty with a space character. Next, we call update tile for this position to update its appearance on screen. Now, Pacman has officially vacated the premises. Once the old position is cleared, we update Pacman position to the new position. Think of this as physically moving Pacman to his new location on the grid. From here on, this new position is where Pacman now lives. Now that Pacman has moved, we need to mark his presence on the grid. Here, we use the character P to represent Pacman in his shiny new spot. Finally, we call update tile for the new position. This ensures that Pacman's new tile looks correct, whether it's showing Pacman, dots, or an empty space. And just like that, the visuals on the screen now match the logic in our grid. And there you have it, this method keeps Pacman moving seamlessly across the board. It clears his old spot, updates his position, and refreshes the visuals to reflect his new home. With this in place, Pacman is officially ready to chomp his way through the maze, one tile at a time. Let's go, Pacman, those dots won't eat themselves, and that's where he moves. Since every old position of Pacman is overwritten with an empty character, it looks as if he eats the dots and moves on. Cool, isn't it? But I see two problems. First, it always looks like he's looking straight ahead, no matter which way he moves, and the second is that he can also move through walls and there's no boundary for him. Since this is not wanted and also triggers an error, that will be the first thing we want to fix. Let's create another method for this. Alright, this method is the bouncer at the door. It checks if Pacman, or anything, really, is allowed to step onto a specific tile. Let's break it down and see how it works. The job of this method is simple. It takes in new position, which is a point representing the tile Pacman wants to move to. Then, it evaluates whether that tile is walkable, or in other words, if Pacman can legally step onto it. First, we grab the size of the level grid. Here, rows is the number of rows, and cols is the number of columns in our grid. Knowing the grid size helps us validate whether the position is even inside the game board. Next, we check if the new position is outside the grid. The if statement condition ensures that Pacman doesn't wander off the edges of the maze. If the new position is out of bounds, we immediately return false. Translation? Nope, Pacman, you're not going there. If the position is within bounds, it's time to check what's on the tile. Here, we fetch the tile character at the new position. This could represent walls, dots, ghosts, or even special features. This line checks if the tile is one of the following. A dot, Pacman loves these. An empty space, free real estate for Pacman. A ghost, yes, Pacman can move onto a ghost tile. If the tile matches any of these, the method returns true, meaning the tile is walkable. Otherwise, it returns false, meaning it's a no-go. And that's how this method ensures Pacman stays in safe and playable areas. It keeps him inside the maze boundaries and checks if the tile is friendly before allowing the move. Thanks to his walkable, Pacman won't be climbing walls, or flying into the void anytime soon. Let's keep him on track and chasing those dots. This looks better. Pacman can eat the dots but can't go through a wall. But he's still looking in the wrong direction and not where he's going. And of course it's a bit strange that he can eat the ghosts just like that. But one by one, let's improve the movement of our hero first. For this we need another variable to capture the rotation and some other changes. But see for yourself. And don't worry, I'll explain every step later. It is important to me that you understand everything so that you can make changes yourself later. Now let's add some style to Pacman's moves. This section is all about making sure Pacman faces the right direction while munching dots. Let's dive in. As you see, we created already a new variable Pacman rotation angle that we fill with data in this method. We've got a little block of if-else magic here that adjusts Pacman rotation angle. This determines which way Pacman's mouth is pointing, up, down, left, or right, depending on the direction of his movement. And hey, Pacman needs to look cool while gobbling up dots, right? This means Pacman's new position Y is smaller than his current position. Translation? He's moving up. In this case, we set Pacman rotation angle equals 270. Why 270? Think of it like a compass. 270 degrees points Pacman's mouth upwards. Here, Pacman's new position Y is larger than before, which means he's moving down. We set Pacman rotation angle equals 90 because 90 degrees is pointing straight down. It's like Pacman saying, down we go. This means Pacman's new position X is smaller, so he's moving left. Set Pacman rotation angle equals 180, this flips his mouth to face left. He's got his eyes on the dots in that direction. Here, Pacman's new position X is larger, meaning he's moving right. We set Pacman rotation angle equals 0 because that's the default, Pacman's iconic position, facing right and ready to roll. This little logic block is the secret sauce that makes Pacman come alive. It keeps his movement dynamic, his mouth pointing in the direction he's heading, and the gameplay immersive. After all, nobody wants a backward-facing Pacman, he's got to lead with his mouth. And there you have it, a neat rotation mechanic that ensures Pacman's always facing the right way. Whether he's heading up, down, left, or right, he's got his eye, or mouth, on the prize, those tasty little dots. Yum! Now that we have the rotation depending on the running direction, we have to change the Pacman graphic to visualize it. To do this, we extend the Generate Pacman Image method with a parameter that we can pass later. With this parameter we can rotate Pacman in the desired direction. This only requires a single line of code. Really simple, isn't it? Finally, we just have to make a small change in the update tile method that calls our Pacman image and we're done. Time for a test, I would say. It looks much better now, doesn't it? I'm sure that Pacman feels more comfortable now because he doesn't walk around so stupidly without looking forward anymore, right? Of course it wouldn't be bad if we get points for every dot Pacman eats and it is also displayed, or what do you think? Let's get started. For this we create a new variable called score and a new method that takes over the update. We then increase the points in the move Pacman method for each dot he eats. But one by one, see for yourself how easy it is. Alright, it's time to bring some bling to our Pacman game. This section creates a neat and tidy UI element to keep track of the player's score. Because, let's be real, scoring points is half the fun. Here's how it works. First, we create a label object and give it a name, score label. Think of this as the game's little announcer, constantly updating the player's score. It's like Pacman's scoreboard, but cooler. This line sets what the label will display. We use string interpolation to show the current score value dynamically. So, every time you chomp a dot, this label will cheerfully tell you your updated score. Here, we decide where the label will appear on the screen. We use 10 for the x-coordinate, so the label is slightly padded from the left edge. For the Y coordinate, we calculate the bottom of the game grid by multiplying the number of rows, level grid. Get length 0, by tile size, and then add 10 pixels for padding. This ensures the label is neatly placed below the game board. Now we make sure our label looks as sharp as Pacman himself. Auto size equals true. This allows the label to automatically resize to fit its text. No awkward cropping here. This sets the font style to bold, using a classic and readable typeface, Arial. It's clean, bold, and screams, "Look at me." Finally, we add the label to the Forms controls. This makes it part of the visible UI so it shows up right below the game grid, ready to track your score. Why it's awesome. This little piece of code is the unsung hero of your Pacman game. Without it, how would players know how many dots they've devoured? It's functional, it's stylish, and it's perfectly positioned to keep players glued to their score. And that's how we set up a simple yet effective UI element for tracking the score. Next time someone brags about their Pacman skills, they'll have the numbers to prove it, thanks to this nifty label. It looks pretty good, but it does not yet show the correct score. We also don't get any extra points when we eat dots. We can fix this with a small change in the move Pacman method. Alright, let's talk about how Pacman racks up those sweet points while munching his way through the maze. This section ensures the score goes up when Pacman does what he does best, eating dots. Here, we check the tile at Pacman's new position on the grid. Remember, new position is where Pacman is headed, so we're essentially asking, what's on this spot? Is it a dot? A ghost? Empty space? This single line is the detective of the game, it sniffs out what's about to happen. Now, we check if the tile contains a dot. Dots are represented by a character on our level grid. If the tile is a dot, then Pacman has just eaten it. Nom nom. Time to reward the player. Every dot Pacman eats is worth 10 points. So, whenever he lands on a dot tile, the score goes up by 10. It's a simple rule but oh so satisfying when you see those numbers climb. This is where the magic happens. After increasing the score, we update the score label on the screen to reflect the new total. This finds the first label in the Forms controls. Since our score label was the first and only label added, this works perfectly. We use string interpolation to set the label's text to display the updated score. The player gets instant feedback, no delays. With this functionality in place, Pacman isn't just moving around aimlessly, he's playing for points, and the player knows it. That little dopamine hit from seeing the score go up? Priceless. But what is that? There seems to be no end. Even when all the dots are eaten, the game continues and nothing else happens, no message that it is finished or a jump to another level. This is of course very frustrating for the player in the end. Let's change this next with a small method. Alright, let's talk about the ultimate goal of Pacman, clearing the maze of all those delicious dots. This part of the Move Pacman method ensures the game knows when you've won and celebrates your victory. This line calls the dots remaining method to check if there are any dots left in the maze. Dots remaining is like Pacman's personal inspector. It scans the entire game board to see if there's a single dot still hanging around. Here means not, so the condition is true if no dots remain. In other words, Pacman's job is done. After congratulating the player, the game exits by calling application exit. This closes the application cleanly, bringing the game to a satisfying conclusion. The return statement ensures no further code in the Move Pacman method runs after the game ends. It's a clean and respectful exit, a proper bow after a victorious performance. Think of it like Pacman scanning the entire maze in super speed mode, checking every spot to see if it contains a dot. Each tile is represented as a char, and the loop looks at one tile at a time. If a tile contains a dot, the method immediately returns true. This means, yes, dots are still remaining in the maze. The loop stops as soon as it finds the first dot, it doesn't bother checking the rest of the grid. Efficient, right? This means the maze is completely clear, no dots remain, and Pacman's mission is accomplished. This combination owes the final confirmation that the player deserves to win. Why it's important: dots remaining and the victory check ensures the game knows when it's over. It gives the player a sense of accomplishment and makes the game loop feel complete. Without it, you just keep playing endlessly, wondering if there's any point to it all. With this functionality, we've added the cherry on top of our Pacman game. It's not just about moving around or eating dots, it's about achieving victory and celebrating it. That's what makes a game satisfying and memorable. However, it is still possible to eat the ghost without harming yourself. Let's fix that next. To do this, we create another query above the dots remaining method that triggers a new game over method if Pacman's position overlaps with one of the ghost positions. See for yourself. Alright, buckle up, because we're about to cover one of the most thrilling parts of our game: what happens when Pacman and a ghost cross paths. This snippet is the heart stopper of the Move Pacman method, where Pacman either dodges danger or gets caught. Let's break it down. Here's where the game gets intense. Ghost Positions is a collection that tracks the current positions of all the ghosts in the maze. If Pacman's current position matches any ghost's position, it's game over. Think of this like a radar system. If it detects a ghost in Pacman's exact location, we're in trouble. Now, if a collision is detected, the game over method is called. This is the code equivalent of Pacman screaming in terror and the game saying, "Alright, that's it, time to end this round." Once a collision is detected and the game ends, there's no need to process the rest of the Move Pacman logic. Return ensures we stop right here and don't waste time updating tiles or checking anything else. It's like slamming on the brakes when a ghost pops out. So, to wrap it up, this snippet is all about keeping Pacman on his toes, or wheels, or whatever he has. It's the dramatic moment where a single step in the wrong direction could spell disaster. Without this, there's no challenge, no stakes, and no game. And trust me, when a ghost catches you, it's a mix of heartbreak and motivation to try again. Now it gets a little more difficult for Pacman. A collision with a ghost ends the game. But of course it would be better if the ghosts also moved and floated around the maze, wouldn't it? Let's take care of that next. Let's create a timer variable and a new method called initializeGhostTimer, and then we'll see. Our code is where the ghosts come to life. It's time to introduce the ghost timer, the engine that keeps those pesky ghosts moving around and making Pac-Man's life a whole lot harder. Let's dive in. This method is like the ghost factory. Here's where we set the gears in motion for those little terrors. We create a new timer object, the backbone of our ghost movement system. Think of it as a ticking clock that tells the ghosts when it's time to take a step. Here's the pace. The interval is set to 500 milliseconds, which means the timer ticks twice a second. Every tick is a chance for the ghost to creep closer to Pac-Man. Adjust this interval, and you'll make the ghosts move slower or faster. Perfect for tweaking the game's difficulty. This line hooks the timer to an event handler. In simple terms, every time the timer ticks, the code says, "Hey, run the ghost timer _tick method now." It's like ringing a bell that wakes the ghosts up. And here we flip the switch. This starts the timer and sets the ghosts in motion. No going back now. It's ghost party time. Ghost timer tick is an event handler. It gets triggered automatically by the timer, kind of like an alarm clock going off every half second. Move ghosts. This is the key line here. Every tick of the timer calls the move ghosts method, which contains the logic for making the ghosts shuffle around the game board. Without this, the ghosts would just sit still, totally ruining the suspense. This system is what keeps the game dynamic and exciting. It ensures the ghosts aren't just static obstacles but active, menacing threats that follow their own rhythm. Alright, it's time to dive into one of the most exciting parts of the game, moving the ghosts. This method gives the ghosts their unpredictability and keeps players on their toes. Let's break this down step by step. We start by creating a random object. Why? Because ghost movement needs to feel unpredictable. Imagine if they followed a fixed path, it wouldn't be nearly as fun or challenging. With this randomizer, we give the ghosts a mind of their own. This is our temporary memory bank to store the new positions of the ghosts after they move. It keeps things clean and organized as we calculate their next steps. Here, we loop through each ghost's current position. It's like saying, alright, ghost number 1, what's your next move? Ghost number 2, you're up next. This ensures all ghosts get a chance to shuffle around during each timer tick. We create a copy of the ghost's current position. This way, we can calculate its next step without immediately overwriting the original position. The random next 4 generates a number between 0 and 3. Each number corresponds to a direction. 0 equals move up. 1 equals move down. 2 equals move left. 3 equals move right. Basically, every ghost rolls a digital dice to decide where to move next. It's chaos, but it's fun chaos. Now, we update the ghost's position based on the random direction. If the dice rolls 0, the ghost moves up by decreasing its Y value. If it's 1, it moves down by increasing its Y value. 2 makes it go left, and 3 sends it right. Simple, but effective. Here's the fun part, can the ghost actually move to its new position? Is walkable new position. This checks if the new position is valid. No walking through walls or other obstacles. If walkable, the ghost moves to the new position, and we store that in new ghost positions. We redraw the ghosts on the board with redraw ghosts. Finally, we mark the new position on the level grid as a ghost tile, G. If it's not walkable, the ghost stays put, and we just add its current position back into the list. No cheating for these ghosts. Why this matters? This whole method adds the dynamic element of uncertainty. Ghosts don't just sit still, they roam around the map unpredictably, making the game much more thrilling. It balances simplicity, a dice roll for movement, with strategy, only moving if it's allowed. This randomness keeps players on edge, especially when ghosts start closing in on Pacman. Move Ghosts is the brain behind ghost movement, ensuring every ghost gets a random new position. It calculates the moves, checks if they're valid, and updates the board accordingly. This method gives the game that classic, suspenseful Pacman feel where you're always one step away from danger. However, there is still something missing in the method, and we still have to fill the redraw ghost method with code before we can test it. So let's get started. Let's finish up the ghost movement logic and explore how we bring these spooky creatures back to life visually on the game board. This is where everything comes together. This line right here is the grand finale for ghost movement. Once we've calculated where each ghost wants to go and verified that the positions are walkable, we update our main list, ghost positions, with the shiny new positions from new ghost positions. Think of it like this, the ghosts were planning their moves in a temporary draft, and now we're publishing their final positions into the official game board. And now, the magic moment, we call the redraw ghosts method. This method ensures that the new ghost positions are actually visible on the game screen. Moving in silence is no fun, let's make sure the ghosts show off their spooky moves. We loop through every ghost's updated position. It's like saying, okay, ghost number 1, where are you now? Ghost number 2, let's update you next. For each ghost, we call the update tile method to refresh its visual representation on the game board. It's like putting on a fresh coat of paint for the ghost's new spot. Redrawing is a critical step in game development. Without this method, your ghosts might move around in the game's logic, but the player would never see it. Talk about frustrating. By redrawing, we synchronize the game's internal state, where the ghosts are, with what the player sees on their screen. This creates a seamless and immersive experience. Oh yes, that looks quite different now. The ghosts move through the labyrinth and find their way at random. Perfect. But what's the problem with the ghosts eating our dots? We have to prevent that next, don't we? Let's get started. Let's create a new variable for this. To do this, we use a new variable in which we save the position for all dots. The best place for this is the method load level. Here we can quickly and easily fill our variable with the necessary data. We will fill the variable later with other characters to protect it from the ghosts. But step by step. After we have saved all the dots in our list, we can continue with a small change in the moveGhost method. We're diving into an incredibly important part of the ghost movement logic. This update ensures that the tiles ghosts leave behind return to their original state, whether that's a dot, a special tile, or just an empty space. Let's unravel this logic step by step. First, we declare a variable found_tile and set it to false. This will help us track if the ghost's current position matches one of the tiles stored in our trusty original tiles dictionary. Then, we loop through every entry in original tiles using a for each. For every key value pair, we ask, hey, does this tile's position match the ghost's current position? If it does, we set found_tile to true. Bingo, we've got a match. Now that we know the ghost was standing on a tile that belongs to the original tiles collection, it's time to restore the tile. If the original tile was a dot, we restore it to a dot. Otherwise, we assume the tile was just an empty space, and we restore that instead. This ensures the game board remains true to its design, even after the ghosts roam all over the place. But wait, what if the ghost's position wasn't in the original tiles dictionary? That's where this check comes in. If found_tile is still false, it means the ghost moved to a tile that wasn't part of the original set of special tiles. In that case, we default to setting the tile back to an empty space, dot. This catch-all ensures that no ghost leaves the board in chaos, everything is restored neatly behind them. This logic is crucial for keeping the board accurate and fair. Imagine if a ghost moved over a dot or a special tile and erased it permanently, total chaos. By restoring tiles to their original states, we keep the game running smoothly and preserve all those delicious dots for Pacman to munch. Of course, we then also have to remove all the dots Pacman has eaten from the list. We can do this quickly and easily at this point. So everything is clear. Let's test it out. Great, that looks really good. The ghosts are moving and only we can eat our beloved dots. But the fact that we die immediately when we touch a ghost is also a bit stupid. We need something like a superpower pill. Let's just put it in now that we're pros. See for yourself how easy it is to add something to the game. Step 1 is to add a new character to the map. We'll use an S for superpower pill. We can simply add this anywhere on our map. As new variables, we create a bool that indicates whether the power mode is active or not and a timer that later gives us the superpower for a certain period of time. Then we use the load level method to add the S to our original tile so that it can't be eaten by the ghosts. Of course, the query in the move ghost method should not be missing to restore the tile if a ghost runs over it. So basically the same as we did for the dots. So that we can also see the super pill, it must of course be displayed in the update tile method with a new image. And that's it, at least almost. Now that we have finished our new method for generating the image of a superpower pill, it's time for another test. And there it is, the beloved pill. But what's this? I can't eat it, and even worse, it's blocking my way. But don't worry, after a small change in the is walkable method it will be fine. Yes, it looks a lot better now, however it still shows no change on us, no superpower to be felt. Too bad. But we'll manage that too. The first step is an extension in the move Pacman method, just below the increase of points after a dot tile. Here we check whether it is a tile that we are eating. If so, we throw it out of the original tiles and call a new method activate power mode. I'll show you what it does later, let's fill it with code first. Pacman champions, now it's time to supercharge our gameplay with power mode. This is the feature that makes Pacman temporarily invincible and ready to gobble up those pesky ghosts. Let's break this down and see how it all works. We kick things off by activating power mode with a simple flag, is power mode equals true. This tells the game, hey, Pacman's in beast mode now. While this flag is active, the game will handle things like letting Pacman chase ghosts instead of running away. This one line flips the script and makes the ghosts fear Pacman for a change. We create a new timer object, and here's the cool part, we set its interval to 10,000 milliseconds, or 10 seconds. This means Pacman's power mode will last for exactly 10 seconds before wearing off. Now for the magic. Using the tick event of the timer, we define what happens when those 10 seconds are up. When the timer ticks, we set his power mode back to false. Pacman's superpowers are now deactivated, and he's back to being cautious around those ghosts. Finally, we stop the timer to reset everything for the next time power mode is activated. To see that the power mode is active, The easiest way is to make a change in the update tile method and load a different image depending on our variable. To do this, we make a copy of the generate Pacman image method to create an image of an angry Pacman. Here we simply change the color from yellow to red and that's it. Let's take a look at angry Pacman. Yes, it looks really good. However, he still doesn't have the ability to defeat the ghost. There's probably another change needed. The easiest way to do this is to adjust the ghost collision part in the move Pacman method. Here, if the power mode is active, we simply call up another method instead of the game over method. So if the power mode is on, we call the new created method remove ghost. And yes, that makes exactly what you think. Alright, folks. It's time to talk about sweet revenge. Let's break down how our Pacman game handles eliminating a ghost when power mode is activated. This method is called remove ghost, and it's all about clearing those pesky spirits off the board. Let's dive in. This line says, "Hey, ghost at this location, you're out of the game." It removes the ghost's current coordinates from our ghost positions list, effectively taking it off the map. Here, we're setting the grid tile at the ghost's location to a blank space. It's like Pacman just erased the ghost from existence. This keeps our grid data accurate and ensures the ghost doesn't magically reappear. Now, it's time for a little cleanup. We call update tile to visually update the grid. This ensures that the spot where the ghost once was is properly refreshed on the screen. No ghost leftovers allowed, just a clean, ghost-free tile. Whenever Pacman eliminates a ghost, we add 200 points to the player's score. It's the ultimate reward for outsmarting those sneaky ghosts, and it gives players a real sense of accomplishment. Let's change the position of these line to a position after our call to remove ghost. Because if we get a ghost, the score will directly reflecting to our label. So time for another test. Yeah, looks really cool. Now it's working and we can destroy the ghost after eating our power pill. See how angry Pacman looks. Before we go on, let's try to structure our code in different regions. So one for helper methods, one for image creation, and so on. That is not really needed but makes it easier for long code to find the right place for any updates later. So looks now really structure or? Let's implement another feature for the game. What do you think about 3 lives for Pacman with 3 images that show the count to us? So if we hit by a ghost and we not in power mode, we lost a life and can go on until all lives are gone. And we can refill the lives with another power up called fruit. We can use the F for it in the map. For this we need 2 new variables. A counter from type int and an array of picture boxes for the icons. If that is done, we can create the same stuff that we used for the power pill. So first add another line to the load level. There we can add the S tile locations to the original tiles to prevent that they are eaten by the ghost. If that is done, we can add the F tile to the is walkable method that we can walk to this tile. If that is done, we need of course also to add the F to places in our map where we want the fruits. And add the F to the update tile method together with a new method generate fruit image for the visualization. So you see it's in general the same for all add-ons that you need and easy for you to add more after this tutorial. You have the power. Let's bring some juicy fruits to the Pacman grid. This is the generate fruit image method, and its job is to draw a fruit image dynamically using graphics. Think of this as giving your game a tasty little bonus for Pacman to munch on. Let's break it down step by step. First, we create a bitmap the size of a single tile using tile size. This acts as our blank canvas where the fruit will come to life. Then, we create a graphics object from the bitmap. Think of this as picking up a digital paintbrush to start drawing. Next, we paint the main body of the fruit, a big red ellipse, right in the center of the tile. The dimensions ensure it's circular and fits snugly within the tile. Now we have the meaty part of the fruit, cherries. Here comes the shine. A smaller pink ellipse is drawn on top of the red body, slightly offset toward the center. This gives the fruit a glossy, realistic look, like it's fresh and ready to eat, glowing star. Now, every fruit needs a stem, right? We add a small green rectangle at the top of the fruit, giving it a cute little handle for Pacman to grab, symbolically, of course. Finally, we finish it off with a triangular leaf sprouting from the stem. The point defines the three corners of the leaf, and fill polygon fills it with a vibrant green color. It's the perfect finishing touch for our fruity masterpiece. And voila! We return the completed bitmap. This image will now represent the fruit in the game. Whenever Pacman encounters it, he's sure to feel rewarded. So now we see our fruit is there and we can eat it. Looks very cool, or, how do you think? Feel free to share your thoughts in the comments about that fruit or any other function. Let's create now the live icons for the game and also the function to use the lives and refill it using the fruits. We start by creating an array called life icons. Its size is based on the number of lives Pacman has, which is stored in the lives variable. Each element in this array will represent one life. Next, we loop through all the lives. For every life Pacman starts with, we'll create one corresponding icon to display on the screen. Now, for each life, we create a new picture box, a small square that acts as a container for Pacman's life icon. Set the size, each icon is 25 by 25 pixels. Set the position, we horizontally offset each icon by 30 pixels, starting from a base position of 150. The vertical position is calculated to align just below the game grid. Set the image, we assign a mini Pacman image, using the generate Pacman image method with a rotation angle of 0 degrees. Set the background, we use a black background to blend with the game's theme. Finally, we add the picture box to the form so it's visible on the screen. This step ensures each life icon is drawn as part of the game interface. So that looks pretty good. Now let's implement the last part for this, to house the lives if we have one, and also to refill it using a fruit from the map. The implementation is nearly the same than the power mode tile. First, we remove the fruit tile's position from the original tiles dictionary. Because once Pacman eats the fruit, it's no longer part of the game grid, it's gone, devoured, and can't come back. And then we call the restore lives method to restore our lives. This is quit easy and loop throw all lives after set it back to 3. Then all picture boxes are set back to visible to see all 3 of them. That's all. The last step is also to modify the game over method. Because if we have a live left, then it's not the end. Now, let's break down the game over method. This is where the drama unfolds and Pacman faces the ultimate challenge. Is it truly game over, or does Pacman get another chance to rise again? Let's find out. First, we start by reducing the number of lives. Yep, Pacman just lost 1 life. But hold on, the game isn't over yet. If there are still lives remaining, this means Pacman gets another shot. Here's what happens in that second chance. We take the corresponding life icon from the life icons array and make it invisible. This is a visual cue for the player, they've just lost one of their precious lives. We clear Pacman's current spot on the grid. Then, we place Pacman back to the starting position at 1, 1. We call the redraw game board method to update everything visually so the player knows Pacman is back in action. But what happens when Pacman runs out of lives? It's the dreaded game over. Here's what goes down. Stop the ghost timer. The ghosts stop moving because the game has officially ended. A dramatic pop-up lets the player know their fate. This message is the final nail in the coffin, better luck next time. The game gracefully shuts down. So, the game over method does an amazing job of managing both outcomes, giving Pacman another chance when lives are left, or ending the game in true Pacman fashion when the ghosts win. It's simple, effective, and keeps the player on their toes. Now, let's dive into the redraw game board method. This is where the entire game board gets a fresh coat of paint. Whenever we need to refresh the visuals, whether it's because Pacman moved, a ghost did something sneaky, or a tile updated, this method takes care of the heavy lifting. We start by looping through every single row and column of the level grid. This nested loop is the engine behind the board update. It ensures every tile is individually checked and refreshed. For each specific tile, we call the update tile method. Now, remember, the update tile method is where all the magic happens. It decides what each tile looks like based on its current state in the grid. Whether it's a wall, a dot, Pacman, or a ghost, update tile ensures the visuals stay accurate and up to date. So essentially, the redraw game board method is like hitting the refresh button for the entire game map. It's efficient, simple, and makes sure that the player sees the most accurate version of the game at all times. And there it is, your very own Pacman game. We have a level system that you can expand quickly and easily using a text file. You can control Pacman and he always looks in the direction he is going. The ghosts move independently and can hit Pacman. Pacman has a points and life system with visual display. As an add-on, Pacman has his power pill, which makes him a superhero, and he can replenish his lives with fruits. Not bad at all, or what do you think? Let's quickly add two little things. First, we change the appearance of the ghosts with a small update and we add a quick and easy sound for Pacman. This should always be heard when he eats a dot. So only add these lines to the ghost image creation and you see direct acknowledge in the game. This makes it more fun, or? Feel free to try different lines or values or use your own images here. The play.sound method adds that satisfying audio feedback when Pacman munches on a dot. Here's how it works. We need to add a WAV file to our project resources that we can use for this. After that, we create a sound player object. Think of it like a virtual DJ, ready to spin a specific track. The sound file it plays is stored in the game's resources, under the name dot. That's the chomping sound effect we hear every time Pacman eats a dot on the board. This line tells the sound player to fire off the sound. No delays, no loading screens, it just goes. We call this method each time Pacman gets score for the dots in the move Pacman method. Let's check if it's working. And there you have it, folks. We've built our very own Pacman game from scratch, adding every feature, every sound, and every thrilling detail step by step. From munching dots to dodging ghosts, and even activating power-ups, this game is ready to challenge anyone who dares to take it on. Take a moment to sit back and admire what we've just accomplished. You've transformed lines of code into a fully playable game, a true classic brought back to life. Now, remember, coding isn't just about writing lines of text, it's about creating worlds, experiences, and, most importantly, fun. Whether you're here to learn, improve your skills, or just love Pacman, you've made something incredible today. So what's next? Customize your game. Add new levels, throw in some crazy power-ups, or even design your own ghost AI. The possibilities are endless, and the best part? You're the game designer now. I prepared also some other maps using a text file for you. What do you think about that? Cool or? And really easy to create. So feel free to create your own level for Pacman. Thank you so much for coding along with me. If you enjoyed this tutorial, don't forget to leave a like, share your thoughts in the comments, and subscribe for more awesome projects like this one. And if you've made your own version of the game, I'd love to hear about it. Let me know how it turned out. Until next time, happy coding, and may your creativity run wild. See you in the next video.